Okay, we are now going to start actually using Matlab to visualize some of these curve-fitting routines. Matlab has a large suite of curve-fitting algorithms in it that we're going to go through, and you can start seeing how these things work and what kind of results you can produce with these curve fits. Okay, so we're going to start off at the beginning with best fits, and we're going to move off to interpolation using polyfits, polyvals, using splines and polynomial fits, and then eventually we'll do a nonlinear fitting routine using what's called the F-min search, which is an extremely powerful algorithm in Matlab that allows you to do some very fancy things. Okay, so I'm going to start off with a set of data, and I've given you the data here. And so this data is going to be, it's just a test set that I want to start looking at. It could be anything. It's just going to be sort of thinking about executing the code. So the XY values are here, and let's just plot what this thing looks like. So I'm going to plot this with black circles so that we can look at the data. All right, so there is the data. Okay, it's a bunch of points ramping up here, it drops to the other end. And so I'm going to start doing a few things with this. So for instance, we're going to start looking at the best fit curves through this data, and what are the command structures to get you your best fit curve. And let's start off with something simple. Let's do this polynomial fit of degree 1. So a least square fit with a first degree polynomial. In other words, a line. I want to do a line fit to this data. What is the best line going through the data? We already worked our way through the problem and how it works in theory. And you know that if you're going to do a line fit through this, you're going to just solve a 2x2 system. Now this is built into Matlab, so we can just take advantage of a built-in routine there. So let's go ahead and program that up in Matlab and to show you the command structure. All right, so those are the data points. And what the command is called polyfit for polynomial fit. And I want to do a first degree polynomial through that data. Okay, so that's what polyfit's going to do. So the way polyfit works is the command is going to be polyfit. Here, let me write it down. You give it the XY data and the degree. Polyfit, X, Y data, line. If you want a parabola, this is quadratic, you put a 2 there. Simple as that. So it's very nice. It executes the algorithm, and what it's going to return to you are the coefficients. In other words, when I think about a line fit, it's AX plus B. There's that A and that B that I have to get back, and this is what it's going to return to me. And so let's call these the P coef. So for polynomial coefficients. Okay? So that's what it's going to return. I send in the data, tell it a line fit, it's going to send back for me the A and the B. Okay? And in fact, if I want to sort of think about how well did my fit work, I could say, well, my A was the first component of this, my B is the second component. And so now I have the A and the B, and now I can plot this curve, this I have the coefficients, so now I can plot the best line fit with these coefficients. Okay? So let's go ahead and do that. So now for actually solving this, I can actually do it very simply by defining an interval that I want to plot this for. So the x values here, if you remember from the curve, they go from 0 all the way to about 7. So I'm going to make a new variable, call it x2, which is going to go from 0 in steps of 0.1 all the way to 7. So I want to now plot my best fit curve, or best fit curve, on this interval from 0 in steps of 0.1 all the way to 7. So it's going to give me a nice curve all the way through a much more refined set of data. In other words, it's going to interpolate a bunch of data points and give them to me here. And polyfit couples very nicely with polyval. And here's how polyval works. I'm going to get y2 out, which is going to be polyval. And what I put in is my coefficients, p coef, and where do I want to evaluate it? So pcoef, it knows it came from polyfit. It knows it's the A and B. So you send it in and you tell it, give me the curve at all these data points, x2, and here are the y values associated with that. Okay? So I'm now going to have x2, y2, which are my new set of data points, which are the best fit line to the data I showed you. Okay? So let's go ahead and take a look at this. So now what I want to do with this plot is put a hold on to it. Oops. And I'm going to add data. So now I'm going to say, okay, now plot x2, y2. Let's plot this in magenta and with a line width of 2 to really make it stand out. So now we're going to have the data and the best fit line. There we go. The magenta curve is the best fit line, and it is truly the best fit line, at least when we're using the definition of error, which is the least square fit error. Okay? So that curve becomes an important curve for us because now it's giving us the slope and the x and y position, so I can get this trend line out. In fact, that's how most people use a lot of this stuff, right? It's like, I know the data points have a lot of variability. What I really want is that trend line. We're going to talk more about trends and variability when we talk about time series analysis, but right now you see, hey, look at that. I got a nice line fit to my data, and now I have a way to predict the future or even the past. I can extrapolate, I can interpolate, and I have a very simple formula to do that. In fact, we can look at the A and the B values are. I can just look in here and say, what's A? A is 0.308. What's B? 2.13. So there's my slope, and there's my offset parameters. I could also do something fancier, which is say, well, actually, I would like not a line fit. I'd like to do a parabola quadratic fit to this function. And so you might want to capture that tailing off phenomenon. All you got to do is change that to a 2 right there. Polyfit, now it's degree 2. You can run this thing. There is your curve. Oop. Okay, so now it looks even better. Oh, by the way, it's always going to look better as you go up in the polynomial degree, at least technically, because now the more degrees of freedom you use to try to get your points closer or your line closer to the data, of course, it's going to drop the error. But it's going to come eventually at a cost, and we'll take a look at that in a minute. Okay, so there's my points. There's my quadratic fit through the data. So now I have this parabolic fit, and I can even compute the error if I choose. And in fact, the error, right, all I've got to do is take what's the actual point, what are my predictions, square it, sum it, divide by the total point, square root. You can apply the formula, and you get your least square fit error out of that. Now, the other thing I wanted to illustrate with this is this idea of polynomial wiggle, which I've talked about, which is obviously as I go up in the polynomial value, it's getting a better and better fit. I mean, it's going to just be the case. You're going to get better and better error. In fact, the one thing I mentioned is if you have a polynomial that matches the number of points you have, then what's going to happen is you're going to get a perfect fit. There's going to be 0 error, technically, but watch what's going to happen to your fitting. Okay, so let's go ahead and come back here and say, okay, I'm going to make up a new variable. N is equal to the length of x. That's going to be the total number of data points. So if I want to do a polynomial that goes through all n data points, then my polynomial to do that is of degree n minus 1. Okay? So I do n minus 1 degree polynomial. So right, a first degree polynomial is a line, goes through 2 points. Okay, so whatever the total number of points, it's n minus 1 here. And so now this will give me a polynomial fit that will go through every data point, and my error will be identically 0. Okay? And let's look to see what happens in this case. Okay. There is my fit. and some really crazy things are going on at the edges. So let me make that a little bigger. So here's the data, and then look at this massive spike that happens here. Now remember that in here, this has something, I can't remember how many points this has. Let's take a look. This thing has 15 points. So the 14-degree polynomial through there, so it has 14 wiggles that it has to go through. Now, why is that important? You can see the consequences of this thing having to wiggle 14 times. It does really well in the middle area here in terms of giving a fit, but at the edges it takes these massive excursion, and that's called the polynomial wiggle phenomena that you get. So if you're going to try to use this polynomial, for instance, to do interpolation, I could say, hey, what's the value of give me an interpolated value at 0.5, or let's say 0.2. You'd go down here at 0.2, you say, oh, what's the value? You know, normally just by the eyeball you'd say it's probably around here somewhere, but this will give you a value of about 40. Way, way off. Does really well everywhere else, and by the way, the error is identically 0. So if you're going to start thinking about, well, how good is the error is perfect. It's just that it gives you a horrible fit to the data. Okay? So this is the real problem with polynomial fitting of data. Typically what you'd like to do is pick out simple trend curves out of high-dimensional data, lines, parabolas, cubics maybe, but you don't want to do this, which is try to fit the entire data set with one function, one polynomial, because you're going to just basically end up in this situation where you get polynomial wiggle. Okay? So now you have this demo of polynomial wiggle and its sort of deleterious effect on data analysis. And it's not a good thing to be playing around with. But however, you know, if we come back down to simple things like, you know, parabolic fits, it's going to give you the right kind of, you know, trends and behavior. And this is exactly where you want to start using such methods.